given by one of the organizers. Aparna Bhaskaran will tell us about self-propelled particles from microdynamics to hydrodynamics.
While waiting for the pointer, I want to thank you all for coming to our meeting, and I hope you're having fun. I'm going to speak today about some work that Christina Marchetti and I have done here at Syracuse University. I'll begin by telling you what the scope of today's talk is. In the past couple of days of this conference, we have heard a lot about large-scale collective dynamics in self-propelled particles. Okay? And we have also learned that this large-scale collective dynamics originates from interactions. For the purposes of this talk, I'm going to be interested in only physical interactions. Okay? My objects don't have eyes or cannot sense chemical gradients, but they are still physical objects moving through a physical medium. So they will have extruded volume interactions, which would be short-range contact interactions, and they will interact through the medium. They will be long-range hydrodynamic interactions. Okay? In particular, I want to ask, how does self-propulsion modify these interactions, and what is the consequence of this modification on the large-scale collective behavior of these systems? Okay? And I'm going to ask and answer these questions in the context of simple model systems, which are universal in the sense that they have everything that I want them to have, but are simple enough that I can make analytical progress. Okay? So I'm going to consider two model systems. First, I'm going to be talking about self-propelled rods sitting on a substrate. And in the context of this model, I will answer the first part of the question as to how short-range interactions are modified and what is the consequence to the collective physics. Then I will switch gears and talk about a low Reynolds number stroke average swimmer living in a viscous fluid and ask, how does the activity-induced hydrodynamic interactions change the collective behavior of the system? Okay? Now, plowing right through to the first part of the talk, contact interactions. Now, self-propelled particles have asymmetric shape, okay? And they move through a medium, so their dynamics is typically overdamped. So we know from the pneumatic liquid crystal example that Lev just showed us that anisotropic shape extruded volume interaction leads to orientational order in fluids, okay? That is the paradigm I'm going to bear in mind. I'm going to think of a pneumatic liquid crystal and ask what changes when I implement self-propulsion there, okay? And what is the consequence of that change to the large-scale physics? And so I'm going to start with what is a canonical microscopic model for liquid crystals, that is long, thin rods. This is my microscopic model. My medium for this part of the talk is just a passive substrate. What I mean by that, it is an infinite momentum sink, and all it does is exert a friction zeta on the particles moving through it. Okay? Then my particles are long, thin rods. Here, in particular, I'm in 2D, so they are capped rectangles. They are head-tail symmetric. They are actually real rods, but I break the head-tail symmetry by saying that a force F acts along one direction of the long axis, and that will be the head of my rod from this point on. That will give it a self-propulsion velocity that is pinned to the long axis of the rod. The interactions in this system are extruded volume interactions. What that means is that the rods interact with each other through energy and momentum conserving collisions. Everything else is white noise. So I don't have anything else in this problem except uncorrelated white noise. So what are the parameters of this model system? The parameters are the self-propulsion velocity, which is the force over the friction. And then there is the noise amplitude of the white noise. I just call it a temperature. I associate with it a non-equilibrium temperature and call it kBT. And then there's the length of my particle L. So this is my model, and then I build my theory. So what is my starting point? My starting point is Langevin equations for the center of mass and orientation velocity of each of my rods. Okay? A Langevin equation says the time derivative of the velocity is, there is the self-propulsion force, there is interaction with all other rods, then there is noise. Together with that, there is friction with the substrate. Okay? From here, I can use the systematic tools of non-equilibrium statistical mechanics and do a step-by-step procedure that will result in an equation for the concentration of rods at a point R, as shown in this picture, oriented in a direction you had. Okay? That equation is called the Smoluchowski equation and is a well-characterized, well-studied equation for liquid crystals. Now what we do is write down the same equation for self-propelled particles. The equation looks like this. For reference, so that we know what's different, I put the liquid crystal equation up on top, and then this is the new equation we get. All the terms that are boxed in red are the new terms that come about because of self-propulsion. Now let's walk through these equations and see what each of these terms are. The first is the obvious term. There is a convective mass flux along the orientation of each particle. That essentially means if I'm pointing in some direction, I'm going in that direction with a velocity v0. Okay? Then I have these terms that are diffusion terms. A rod-like particle, when it diffuses through a medium, the diffusion is anisotropic, right? Because the friction is smaller if I move along my long axis rather than perpendicular to it. So I have anisotropic diffusion. What self-propulsion does is enhance this anisotropy. What happens is the diffusion along the long axis of the rod is enhanced by the self-propulsion. And that's again easy to understand by saying that what is diffusion? It's random walk. And if I'm a thermal particle, I'm random walking with a step size that is friction constant times square root of the temperature. And I take that step in all directions. Now instead I'm a self-propelled particle. So I take a step that is of order V0 along my long axis and of order kBt in every other direction. So I take bigger steps along my axis, and that leads to enhanced diffusion along my axis. Okay? Then I have these terms. In the Smolchowski equation for an equilibrium liquid crystal, you have some forces and torques that come from the excluded volume. Traditionally, they are written as a derivative of an Onsager excluded volume potential. Okay? Now, the way these forces and torques come about is that you have energy momentum conserving collisions between these rods, and those energy momentum conserving collisions happen between rods whose typical velocity is square root of kBt, and the direction of that typical velocity is anything. Okay? Now, in addition to that, I have another typical velocity v0 that is pointing always along my long axis. That gives rise to extra forces and torques. And those are these two terms. I can write down an expression for them. They look messy, but the only point to note is that they build up additional orientational correlations in the system that are actually different from that which you would get from the thermal part of the interaction. So, that's my theory. From that theory, I try to look at the long wavelength physics of the system and ask what are the consequences of the changes that I just described to my theory. I make a list of some consequences, and I will talk about the first two. Okay? Now, if I was thinking of a thermal system of rods, that is head-tail symmetric, so the only kind of order that I can have is nematic. But at the level of my microscopic model, I broke the nematic symmetry by giving each rod a head and a velocity along that head. Okay? But it turns out that the polar order does not show up in the macroscopic physics. So even though each rod is polar, if I look at the collective dynamics of the system as a whole, there is no polar state. That means that excluded volume interaction does not result in everybody pointing in one direction and going in that direction. I don't get flocking from excluded volume interaction. That's one consequence. Now, I do have the isotropic nematic transition, just as I had for my thermal rods, but now the transition occurs at a lower density. This is what we are calling enhanced ordering. And that density scales as the square of that self-propulsion velocity. So the ratio here is self-propulsion velocity to the thermal velocity. Okay? And what I call rho Onsager is the density at which the transition would occur if I just had thermal rods. Okay? And now, this has been seen in a simulation. This is a numerical simulation of a motility assay. A motility assay is essentially a substrate where you have put down some motors that are pinned. The motors reach up, grab short-acting filaments and push them. Okay, this is a simulation of a motility assay, and they see essentially that enhanced ordering as this theory predicts. And given that I have derived the theory from microscopics, I can tell you where that enhanced ordering comes from. Okay, the enhanced ordering comes from the anisotropic momentum transfer that is associated with the self-propulsion velocity. That tau term on my previous equation that said that there is additional angular momentum transfer associated with self-propulsion. This enhanced ordering business comes from that term. Okay. So that's one consequence, long wavelength consequence of a modification to the interactions by self-propulsion. Now let's talk about one more consequence. Another thing that happens in the system is that if you had a traditionally overdamped system, all the modes in the system should be diffusive, right? But in this case, because you have convective mass fluxes associated with self-propulsion velocity, the modes are not necessarily diffusive. There is a region of parameter space where you can get propagating modes in the system. And I show a movie where maybe they have seen this. If it comes up. Okay. This is an experiment done by Doug Durian and Lynn Daniels over at UPenn. And what this is a gas fluidized bed of small rods. Okay? And what they see is compressional waves. In certain regime of the parameter space, they are able to see these compressional density waves just like in the theory.
So they flow gas? Self-propelled?
Yes. And that makes the rods self-propelled. The things rise up and start running. Okay. Now, I already said this. It comes about because you have these convective mass fluxes that are associated with self-propulsion that wouldn't be there if your system was not self-propelled. Okay? Now, there are other consequences which I will not go through, but some other consequences include the homogeneous pneumatic state is destabilized. So you don't have a homogeneous pneumatic state in certain regions of parameter space for the self-propelled system. This is in direct contrast to what you know for traditional liquid crystalline systems. And Fernando Pervani was telling us about this. He has seen this in his numerical simulations where he starts seeing these clumps of rods. And lastly, you can get large number fluctuations. This large number of fluctuations is essentially saying that the fluctuations don't scale the way you expect them to scale in an equilibrium system. And Narayan Menon and his collaborators have seen it in an experiment on vibrated rods. And so what this is an illustration of how the excluded volume interaction changes because of the self-propulsion and how that modifies some long wavelength behavior of the system. Now, I'm going to switch gears and ask a different question. What I'm going to ask is, supposing now the medium was not passive. It did not just exert a friction on me, but it actually responded to me pushing on the medium. Then, what is the effect of the resulting hydrodynamic interactions on the collective behavior? To ask that question, the rest of the talk is going to be self-propelled particles in viscous fluids. Again, let me state the context of what I'm trying to say. In the back of my mind, I'm thinking I'm trying to understand bacterial suspension. Okay? In that regime, given the velocities and sizes of bacteria, I'm at low Reynolds numbers, so mass is unimportant. And basically Aristotle is right. And I'm also going to be interested in length scales that are long compared to the size of the swimmer and time scales long compared to the stroke period. In this length and time scale regime, I don't really need to know everything there is to know about my swimmer. I need to know very less. Okay? So what I'm going to be working with is a stroke averaged model. So I'm going to take a swimmer. This is a cartoon image of an E. coli, and average over the stroke of the E. coli. Then I know that if I look far enough away in the fluid flow, the disturbance will look like that of a forced dipole located at the site of the swimmer. Okay? And that is going to be the model system that I'm going to be working with. As a consequence of this, the only thing that's going to enter into my theory about the swimmer is one question. Is my swimmer a puller or a pusher? Okay? The image on the left is a Chlamydomonas. The image on the right is an E. coli. The Chlamydomonas is propelled by flagella in the front of its body, and hence it pulls fluid in at its head and its tail and pushes fluid out in the middle. While the E. coli, which is propelled by flagella on the back of its body, pushes fluid out at its head and its tail and pulls fluid in the middle. Okay? And that is the only information that is going to enter into the theory about the swimmer. Is my swimmer a puller or a pusher is the only question. Now, let me briefly describe the model that I'm going to consider for this study. My model is a rigid dumbbell consisting of two spheres of radius A head and A tail connected by a massless rod. And these two spheres exert equal and opposite forces on the fluid along their axis. We are at low Reynolds numbers, so the only thing that will happen is that the swimmer will be convected with the local fluid velocity. So the head moves with the fluid velocity at the head, the tail moves with the fluid velocity at the tail. That fluid velocity I have to infer from a Stokes equation. So I have a Stokes equation which contains information about the forces that the particles are exerting on the fluid and also some noise. So there, whatever randomness there is to this propulsion mechanism enters as a noise that goes into the Stokes equation. I'm going to assume incompressibility. I'm going to be in the regime where my system is incompressible. Now, what I effectively do is I solve the Stokes equation for an infinite system and substitute the answer for the fluid velocity at the head and the tail. And that is going to be the microdynamics for my system. Okay? Before I do that, I just want to formulate it so that it looks like standard rigid body dynamics. At low Reynolds number, the point about which the torques on a body vanish is not the center of mass, but rather is the hydrodynamic center. For a dumbbell, it can be defined that way. So what I'm going to do is rewrite this equation as an equation for the motion of the hydrodynamic center and the orientation of the swimmer. Okay? If I do that, then I get equations that look like this. So I have equation for the hydrodynamic center. It is self-propelled. It moves along the axis of the swimmer. It feels some forces due to all the other swimmers in the fluid, and there is some noise. Similarly, the orientation coordinate, this guy, has some angular velocity because of torques exerted by all the other guys in the medium. Okay? One of the things to notice about this equation is that if you look at the self-propelled velocity, it goes as a tail minus a head. That is to say, a symmetric dumbbell does not move. So this is the minimal model for a swimmer. If I took a symmetric dumbbell, it will be a shaker. It will not move. It will exert forces on the medium, but it will not move. Now, just briefly, let me make connection to the nomenclature I mentioned in the 2 slides back about pullers and pushers. Now, I have averaged over the stroke, so that I don't have any flagella or anything here. But for F less than 0, my swimmer is a puller, in the sense that it pulls fluid in at the head, pushes fluid out in the middle, and it's a puller in the sense that the hydrodynamic center is located towards the front of the object with respect to its direction of motion. Okay, that's how the puller business shows up in the stroke average language. Conversely, if I take F greater than 0, that's a pusher, and the hydrodynamic center is located at the back of the object. Okay, and the chlamydomonas falls under this category, while the E. coli falls under that category. Before going on and telling you what the consequences of the hydrodynamic interactions are on the large wavelength physics of the system, let me just show you what the forces and torques look like briefly. Now, what do the forces and torques look like? They are long-ranged. That's going to scale as the size of the system. They are 1 over r square interactions. Okay. The long-range part of the force is pneumatic, in that it doesn't know whether I'm a mover or a shaker. I could be a particle that is just staying there and exerting forces in the system, or I could be a particle that is actively moving through the system and exerting forces. Irrespective of that, my forces and torques are actually the same. So I call them pneumatic. There is a polar part to the torque, the hydrodynamic torque that the swimmers feel, but the polar part decays much faster. It's not long-ranged. Another thing to notice is that the forces and torques are actually spherically symmetric. So if I stand here and then I ask what is the force exerted by every other guy around me, if I integrate over that, that will be 0. In mean field, the hydrodynamic forces and torques will vanish because it's central. I obtained it by solving a Stokes equation. Okay. Now we move on and say, okay, that is my microscopic model. I can again turn the crank and do the theory that I described in the first part to get statistical mechanics description and obtain hydrodynamics. And now I'll tell you a little bit about some of the things that come out of that hydrodynamic description. No ordered states. I can't get a pneumatic bacterial suspension or a polar bacterial suspension with just hydrodynamic interactions in far field. Okay? And if you go back, you see, oh, I have this spherical symmetry, it's going to vanish in mean field, so it's not going to do the right things to give rise to order in the system. So I cannot get an ordered state in a suspension of active particles with only hydrodynamic interactions. But I can get a pneumatic state. I just turn back excluded volume interactions, keep track of the fact that those guys have some shape and hence exclude volume to each other, and I can restore pneumatic order in the system. But as far as we are able to see, it appears that a polar state can be obtained only with external symmetry breaking. For example, chemotaxis. There has to be an external axis given to these guys to get a polar state from just these physical interactions. The rest of the story I will try to summarize in the form of this phase diagram. Okay? On the long axis here, on the vertical axis here is the force F. So the upper part of this phase diagram represents such organisms as E. coli, while the lower part of the phase diagram represents such organisms as the chlamydomonas. So the pullers are over here and the pushers are over there. Okay? And the horizontal axis is the concentration of swimmers in the medium. Now, if I look at the low density states are the ones that are disordered. They are isotropic suspensions of active particles. And I look at tensile swimmers. Okay, let's start with contractile. If I look at the contractile swimmers, as a function of activity, the system goes from being in a stable state to an unstable state. Okay? And this instability is diffusive. There is a diffusive instability in a suspension of contractile swimmers as a function of activity. And this diffusive instability comes about because there is a suppression of longitudinal diffusion. The hydrodynamic force exerted by contractile swimmers on each other is such that they attract each other along their axis. And that leads to a suppression of longitudinal diffusion in the system, and that gives rise to a diffusive instability as a function of activity. On the other hand, if I look at the tensile swimmer, it also has an instability as a function of activity, but that's a scale-free instability. There is no length scale associated with the instability. Simultaneously, all modes on all length scales go unstable. And the origin of that instability is associated with the fact that splay fluctuations are unconditionally unstable in the case of tensile swimmers. And this is something that has been observed in numerical work that Patrick has done, and Santillan and Shelley and people like that. So, in the isotropic state, there are instabilities in both suspensions of tensile swimmers and contractile swimmers, but they are basically different in nature. Now, let's go to the ordered state. Let's increase the density of the suspension so that they are in an ordered state, the nematic ordered state or the polar ordered state. Then, we know from past work from Ramaswamy and collaborators and others that there is a scale-free instability in the system. Again, a system goes unstable on all length scales because of the fact that the long-range torque destabilizes orientational fluctuation. I already told you there is a nematic part of the torque that is long-ranged. It's going to scale as the system size, and that long-range torque destabilizes all fluctuations in the system. And so it has been referred to as a generic instability in the literature because of the fact that it occurs for everybody. Swimmer, shaker, mover, whatever you want to call their cell, it's still going to occur there. Now, it's the same as the instability identified in the phenomenological hydrodynamic equations earlier. But the only additional contribution that comes out of this work for this particular observation is that if supposing I had a time reversal and parity invariant stroke for my swimmer. So I cannot have a time reversal invariant stroke for my swimmer, right? I am at low Reynolds number. If my stroke was time reversal invariant, that means that if I reverse time, I should go with minus V. The Stokes equation is invariant under time reversal, so V should be equal to 0. That's the only conclusion you can come up with. But you could have a stroke that is parity and time reversal invariant. If that is true, then this long range part of the torque is 0. That term is killed by symmetry. And if it is killed, all of the instabilities that I just described here go away. Okay? Now, let me make a few remarks summarizing what I've said so far. What we have done is given a unified description for the hydrodynamics of active liquid crystals, or rather that is the paradigm we have in mind when we are thinking of these active self-propelled particles. We're thinking of them as liquid crystals and asking what is different. We have characterized the nature of fluctuations in the bulk system and given an interpretation for the underlying mechanisms that give rise to these fluctuations. Now, all conclusions hold for all systems in this class because of the fact that the only assumption that goes into any of these calculations is momentum conservation. There's absolutely nothing else that needs to be valid. And if you don't see it, it's because something else is going on, not that this is not there. Momentum conservation is the only thing that you need for all of this to work. Now, then the question is observability. Can you see any of all of this in any system? And the observability turns out to be governed by the Beckley number. Here I have defined the Beckley number as F over C, which is the typical self-propulsion velocity, which is the typical velocity induced in the fluid by the swimmer doing whatever it's doing, divided by the diffusion velocity. Okay? So, if the Beckley number is large enough, you will be able to see all of the phenomena that has been described so far. And now, in the next 5 minutes or so, I will describe to you what are the next steps, what are the systematic approaches that we are taking here at in our group towards nonlinearities and boundaries. So far, all I have told you is about bulk systems, okay, and bulk systems close to homogeneity. One has to go and ask the questions about what nonlinearities do to these systems and what do boundaries do. First, let me tell you a little bit about nonlinearities. In the first part of the talk, we talked about these self-propelled rods, and we derived hydrodynamic equations that describe these self-propelled rods. Okay? I told you a little bit about the consequences of those hydrodynamic interactions for the bulk system. What we did next was take those hydrodynamic equations, put it on the computer and solve it with respect to some boundary conditions. This was work done by Shraddha Mishra, a postdoc in our group. So what she found is that if you start with initially homogeneous isotropic distribution, you quickly start getting bands. Okay? The bands are polar order in the band and isotropic state outside the band, and the band propagates with some velocity. So she gets propagating bands in the system. And the nonlinear terms in the polarization equations are the critical driving force behind this observation. Now, we are analyzing this stuff to understand better, but maybe this has been seen in a real system. This is a Motley TSA system of short-acting filaments that Volker will be telling us about at the poster session outside. And he's seeing the same bands. So we're trying to understand if maybe he's seeing this band or not. Or it might turn out that I'm a person with a hammer and everything is looking like a nail, but we are trying to understand this. Now, the next, so I told you about nonlinearities. We are also trying to understand boundaries. Okay, so a bulk system, infinite bulk system is never there. There are always boundaries, and if you are in a fluid, boundaries are very important. Okay, Eric Lauga told us previously that if you had a no-slip wall, then tensile swimmers tend to be anchored parallel to the wall, while contractile swimmers tend to be anchored perpendicular to the wall. Just hydrodynamic interaction with the wall gives rise to this physics. What it also does is it affects the self-propulsion speed. So when a tensile swimmer gets closer to the wall, its self-propulsion speed starts to drop. It starts to slow down. And for a contractile swimmer, if it is facing the wall, it accelerates. That's the crashing into the wall thing that Eric Lauga was telling us about. And if it is facing away from the wall, it begins to slow down in preparation to crash. Presumably, it eventually gets negative. Now, all of this stuff is done with a simple method of images calculation that you use to enforce this no-slip boundary condition at the wall. Okay, you can do more with this method of images calculation. You can take two swimmers, N swimmers, and still do the same analysis, and it turns out it's very colorful. So we are trying to unfold the details of what a wall does to these systems. And that basically brings me to the end of my story. So I will stop here and take questions. Thank you.
Questions? Back.
Yes.
I have two questions. Are you interactions between pairwise?
Could you speak up just a little bit? I'm not able to hear you.
Are your interactions pairwise hydrodynamic?
In the Stokes regime, the interactions are pairwise additive. It's a linear equation.
No. I was wondering only if you have two. Do you have three-body interactions?
How would I get that from the Stokes equation? The Stokes equation is linear. Even if I put n swimmers, I will get pairwise additive interactions, no? No? It's a linear equation. I solve it, so I should get pairwise additive interactions at the end of the day. So yes, my interactions are pairwise additive. That's the short answer to that question. Yes. What was the other question?
So do they come in here?
Okay, so essentially, most of the things that I'm telling you about the microscopic theory is really not valid within 3 swimmer lengths. If they get too close compared to 3 swimmer lengths, most of the stuff that I'm saying needs to be modified, needs to be corrected with short range corrections. That has not been done. So it essentially is a dilute theory.
But you have, say, external volume.
Pardon me?
But you still have external volume interactions.
Extruded volume interactions are there, yes. Volume exclusion is there.
But then they have to cut.
Okay, so there are 2 parts to the story which go with each other additively. Okay, the first part of the story had extruded volume interactions and no fluid. The second part of the story had hydrodynamic interactions but no extruded volume, especially explicitly implemented at the microscopic level. At the microscopic level, my swimmer was essentially a point dipole.
Yes.
Okay, does that make sense?
Yes.
Yes.
So this.
There's some particular angle at which it works.
So the one that you showed is about for the dry example.
Yes, it's for the self-propelled rod dry example. I think it's the same as your bands, though that's not an infinite system.
But the band is polar or is polarly oriented, or you have kinematic order where is the band, and you have isotropic.
We have polar order. The band is propagating with the self-propulsion speed of the particles. Is that correct, Shraddha? Yes. Yeah, so this is the long axis of the band, and the rods are pointing like this in the band, and they are moving with the band. This is a confined system, though. This is not your bulk system.
Oh.
It's not periodic boundary conditions. We have walls, and hence we have a length scale.
considered a quadrupole.
No, it's only a forced dipole. The only way I get quadrupole, I do get quadrupole terms in my interactions, but the reason being that by taking an asymmetric forced dipole, that is I'm taking a big sphere here and a little sphere here and studying the dynamics of the hydrodynamic center, I generate all orders.
Okay.
Okay,
So
even though I
it's
start with the
implied. Okay.
so I do generate all orders and I do have the quadrupolar term in my interactions.
Because
I-
in our measurements, the quadruple term actually is the first leading term for correlation, for velocity correlation.
That is potentially true in the sense that the coefficient in front of the dipolar term goes as the measure of the asymmetric. But the quadrupolar term does not go scale that way. So I can imagine that that might be the more important term for velocity correlations in the system.
Thank you.
So you used Brownian diffusivity, but you also might have to worry about hydrodynamic diffusivity.
Pardon me?
You might also have to worry about
Yes.
hydrodynamic diffusivity.
Yes. Yes.
It's
We
going
just
to be
left
very
it out of
high.
this calculation because of the fact that that's a well characterized thing. Lots of people have worried about it, and I can just go look at a book and figure out how the diffusion coefficient is corrected by hydrodynamic interactions. Right?
Definitely more complicated than that.
It is more complicated
Because
than
you
that,
have-
but I know how to do it is what
Yeah,
I'm
I mean,
saying.
you didn't have Brownian diffusivity, but you still have random rods.
Mhm.
The flow induced by them would be a random field which would create an
Yes.
isotrophic diffusivity. for
Yes.
hydrodynamics.
I see what you're
It might
saying.
be more important than Brownian diffusivity.
That is possibly true, but what this consideration
focal
so far is
line
only the
equation.
active hydrodynamic interactions induced due to the active forces. I see what you're saying. If I have rods in the fluid, I'm going to have induced interaction just because I have rods in the fluid. Right? That part is kind of ignored. I only have the activity related parts here. That is one side.
So you mentioned time reversal and parity
Mhm.
transfer. So what would be a parity transformation for these swimmers?
So you just x goes to minus x maps the head to the tail and the tail to the head. So basically, what transformation takes a contractile swimmer to a tensile swimmer is the time reversal transformation. Right? Time reversal parity. If you do time reversal, the flow at the head will be inverted. And if you do parity, the head will go to the tail and the tail will go to the head.
Okay.
It's exactly the transformation to take a contractile swimmer to a tensile swimmer.
Alright.
Anyway, I think Gareth will say more about it when he talks next. Yes? Yeah, he will say more about it.
Okay. And I might just also make a comment about the pairwise additivity.
Yes.
Since I do some of this stuff too. So with hydrodynamics, if you know the force and you want to find the disturbance velocity, it is pairwise additive.
Yes. The other way is not
If
true.
you knew the velocity and were trying to calculate the force, it's not pairwise
It's not.
additive.
Yes.
So you are capturing those non-pairwise additive things by doing a pairwise additive
Formulation of the thing.
formulation.
Yes. That's a reason to formulate it this way because it's just way messy and I cannot do stack mech with non-pairwise additive things. I see what you're saying.
There are other questions? Okay. Oh, yes.
No, not a question. Some carefully reader noticed that we're missing half an hour of our program. So will you just go about it